Okay, so we're going to do our review here for physics. So it'll be on sound, reflection and refraction, and lenses and mirrors. But I'm going to include one additional problem, which was on the last test, which a lot of you didn't do so well on. So I'm going to go over that first, and that was waves on a string. And basically what we had is, as the name implies, a wave on a string. And so we had the relationship for waves in general, which says that the speed of the wave on the string equals the wavelength times the frequency. So that's wave speed. And that's in meters per second. Lambda is wave length in meters, and F is frequency in hertz, which is 1/seconds, cycles per second. Now that's just for waves in general, but the key thing here, the other two key things, is the wave speed is equal to the square root of F, capital F, over mu, where capital F is the tension, and that has units of newtons, and mu is the mass per unit length. And that's kilograms per meter. So V is the wave speed. And then finally, to get harmonics on your string, so you've got the string attached at 2 points, and it's going to oscillate. The first harmonic is this situation. The ends are the nodes, the middle is the antinode. And it turns out that the wavelength is equal to twice the length. So we have in here this case, for the fundamental frequency, the wavelength equals 2L. So if we use this equation, solve for frequency, it's V over lambda, but in this case lambda is 2L. So you get that for your frequency. So if you go back to the problem that I gave you, so here's the problem. So it says the length of the guitar string that vibrates is 64 centimeters long. So in that particular problem, L was 0.64 meters. The frequency was 643 hertz. And the mass per unit length was 0.341 grams per meter. So that would be 0.341 times 10 to the minus 3 kilograms per meter. Or we could say it's 3.41 times 10 to the minus 4 kilograms per meter. So what I've done there, this changes grams to kilograms, and I've then moved the decimal point 1 space and made the exponent to the negative 4 power. So that's mu. So it says, what's the tension in the string? So if you look at what we have over here, we have frequency. This is the length of the string. So you can see I can calculate V. And once I have V, I can calculate F. Okay, that was what you were supposed to do. Now, if I give you a problem like this, I may give you some different, I might give you different things, and you have to solve it. So I'm not guaranteeing that it's exactly the same problem, but I'm just going to work through this one to show you how you were supposed to work it. So what we do is we say the wave speed is 2L times the fundamental frequency. So we have 2 times L, which is 0.64 meters. So I've converted centimeters to meters. And the frequency is 643 hertz. Now the units here are inverse seconds, so you get meters per second, which is what you would expect for wave speed. So I'm looking in my bag for my calculator. So what do we, 2 times 0.64 times 643, and you get 823 meters per second. So that's the wave speed. And then you have the relationship, wave speed is equal to the square root of the tension divided by the mass per unit length. So if we square both sides, you'll get v squared is equal to F over mu, or F is equal to mu, the mass per unit length, times v squared. So now all we have to do is plug in everything, 3.41 times 10 to the minus fourth kilograms per meter times 823 meters per second quantity squared. Now if you look at the units, you'll get kilograms meters per second squared, because this will cancel out with one of these. So you'll have kilograms meters per second squared, which is a Newton. 3.41 e to the minus 4 times 823 squared. And we got 231 newtons. Okay, so that was how you're supposed to work that problem. I'm going to put another one on the test similar to that. So just make sure you can manipulate those kinds of things. Okay, so now sound. There'll be one on sound intensity. So sound intensity this has units of watts power per meter squared, watts per meter squared area. And we call that I. Now we have this I0, which is kind of like a reference intensity, which is 1 times 10 to the minus 12 watts per meter squared. That's the minimum level that somebody can hear. And we base everything on that. So there's I, the sound intensity level, which is going to be greater than 1 times 10 to the minus 12 if we're going to hear it. We also have decibels. It's just another way of doing it. It's a logarithmic situation. So you have, it's equal to 10 log base 10 of the ratio of the sound intensity level to the reference sound intensity level. So if this were the same, if this were 10 to the minus 12, 1 times 10 to the minus 12, you'd end up with log 1. Log base 10 of 1 is 0, and so you get 0 decibels. If you this was twice, if this were, or not 10 times, if you had 1 times 10 to the minus 11th divided by 1 times 10 to the minus 12, that would be 10. The ratio of 10, log base 10 of 10 is 1, so you get 10. So every time you increase the power by a factor of 10, the decibels increase by 10 units. So what I would do in this kind of problem, I think we talked about it in class, is I would give you, so given, let's say, the sound intensity level, actually I'd probably give you in decibels. So let's say one singer, and we're assuming all the singers have the same volume capacity. Let's say one singer is 74 decibels. So you can calculate the sound level by solving for I. So let's put it in the equation here. So it's 74 is equal to 10 log base 10 of I, which is what we're trying to figure out, over 1 times 10 to the minus 12 watts per meter squared. And decibels don't have units. It's unit. That's kind of like radians. Okay, so what you would do is you'd divide by 10, so you get 7.4 is log base 10 of I over 1 times 10 to the minus 12th watts per meter squared. And then you would take 10 to the 7.4 power So we get 10 to the 7.4 is equal to 10 to the log base 10 of I over 1 times 10 to the minus 12th. Now, one thing is that 10 to the 7.4 power does not equal 7.4. I'm even not even sure how I'd figure it out that way. Anyway, it has nothing to do with that. So you have to actually put that into your calculator. And so you'd take 10, you'd raise it to the 7.4 power using that little, that's on your, if you have a TI calculator, which I think everybody does. So you'd have 10 raised to the 7.4 power. And yes, I get a number here, which I'm going to convert. Well, I'm not going to convert because I'll show you how to do this. So that's the number you get. And that's going to equal I over 1 times 10 to the minus 12th. So what is that? Well, it's 2.4 times, so you go 1, we just count here, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And you can check that out just by, I think if you did 2.5 e to the 7th power and just stuck it in there, you'd get hopefully the same number of digits. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, yeah. Okay, so that's the correct answer. So I've rounded it off here. So now you find out the sound intensity of one singer is 2.5. So that's a nice thing here. You just multiply the coefficients together. 2 times 1 is 2.5. And then you add the exponents. So it'll be 10 to the minus 5. And the units are watts per meter squared. Okay, now the question is, there's two ways I could ask this question. What is the decibel level for 6 singers? Or I could ask, how many singers to exceed, let's say, 84 decibels. Okay, so let's just look at both of these. Well, all you have to do here is, you don't multiply or add decibels together, but you can, if we said I of 6 singers is 6 times I of 1 singer. So in this case, you take 6 times 2.5 times 10 to the minus 5 watts per meter squared, which is going to be equal to, so 2.5 times 6 is 15. So you'd have 15 times 10 to the minus 5th watts per meter squared, or 1.5 times 10 to the minus 4th watts per meter squared. So there I'm changing it to 1.5 because that's the way you're supposed to do scientific notation. And then you can convert that to decibels. So you take 10 times log base 10, 1.5 times 10 to the minus 4 divided by 1.0 times 10 to the minus 12. And then you can just stick that in your calculator. So log 10 times log base 10, log, 1.5 e to the minus 4 divided by 1 e to the minus 12, and you get 82 decibels. Okay, so that's how you do the first kind of problem. Now, how do you figure out how many singers exceed 84 decibels? Well, in that case, what you'd have to do is you'd have to figure out what it is for 84 decibels. Question mark. So what's that? Well, you do the same thing you just did a second ago. So you'd have X, some number. Let's use something other than X. Let's use S for singers. So you'd have S times the sound intensity. Well, first we got to figure out what the sound intensity is for 84 decibels. So we'd have to do the same thing. This is 84. So you'd have, this is the question mark. Okay, so you'd have 84 is equal to 10 log base 10 of x. That's what we're trying to solve for. 1 times 10 to the minus 12. Okay, so you get 8.4 is equal to log base 10 of x over 1 times 10 to the minus 12. And then you do 10 to the 8.4 power is going to be equal to x over 1 times 10 to the minus 12. Because here I'm doing 10 to log base 10. Okay, so 10 to the 8.4 power is 2.5 times 10 to the, let's count them here, 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th. So you'd get 2.5 times 10 to the 12, 8 minus 12 is negative 4. So that would be, that's the decibels, I mean the sound intensity. And then all you have to do is take the, we'll call it, and I said I was going to call it S, and then I called it X. Okay, so let me go back here. Well, no, that's not right. So what we're going to do, yeah, S. So S is going to be number of decibels, or the sound intensity for 84 decibels divided by the sound intensity for one singer, which is 2.5 times 10 to the minus 5. Interesting. Just kind of came out just right. 10. Okay. Now, if it had been, if this number had been 9.5, then 9 would not be loud enough, so you'd have to round up. So you're always going to round up here. So it's unlikely that if I give you this problem, so tweak, that's why it says exceed. In this case, it was exactly 10, so I don't have to round up. Okay, so those are the two possibilities that I may give you. The key thing is knowing how to convert from decibels to sound intensity, knowing that if you have multiple things of the same sound intensity, that you add those together, or you multiply by the number of objects you have. Okay, what else we got? We've got tubes, harmonics. And we had two situations, open at both ends. In that case, what we had is we had a tube. You can just think of me going woo. So what we have is we have a node here in the middle, and we have antinodes at the end. So we get a large variation at the ends, and not so big a variation in the middle, or zero variation in the middle. So this is actually, well, looks more like this. Try like a sine wave instead of that. So you see what we have is we have half a wave. In this case, this is the fundamental. So for the fundamental first harmonic, the wavelength equals 2L, just like it does with the string, wave on a string. Now, we still use V for the speed, but in this case, this speed is the speed of sound, not the, which is, it's not the speed of the wave on a string. So we have the speed of sound, meters per second. And remember, that is, I can either give it to you or you can calculate it if you're given the temperature. It's 331 meters per second times the square root of the absolute temperature divided by 273 Kelvin. So if it's greater than 273 Kelvin speed is going to be higher than 331. If it's less, the other way around. Okay, so putting these together, wave speed equals wavelength times frequency, or frequency equals v divided by wavelength. But we just said here the wavelength is 2L, so you just get v over 2L. It's exactly the same as for the wave on a string, except the speed here is not the square root of f over mu. It's equal to the speed of sound. So that's how you get the fundamental frequency for this kind of open at both ends. And in this case, the second harmonic is 2 times the first harmonic, and the third harmonic is 3 times the first harmonic, etc. So if you calculate the fundamental frequency, you can calculate the harmonics just by multiplying by integers. Now, open at one end, in that case, so here's, it looks the same, but I'm going to emphasize this end's closed. So because it's closed, you can't have any movement of air, and therefore this is a node and this is an antinode. So it looks more like that. And so in that case, the fundamental frequency is such that lambda is 4 times L, because you're going to have to go through here, then up here, and then down. It takes 4 wavelengths to get 4 lengths to get 1 wavelength of the sound. But the same relationship applies. V is equal to lambda f. So f is v over lambda. But in this case, lambda is 4L instead of 2L. So your fundamental frequency for a tube open at one end is half of the frequency of a tube open at both ends, which seems kind of counterintuitive. You think if you're limiting it here, you're making it so go the other way, but that's not the way it works. But because this always has to be an antinode and this has to be a node, instead of the second harmonic is actually going to be 3 times that number. So it's 3v over 4L. And the third harmonic will be 5v over 4L. And so this is 3 times the fundamental, and this is 5 times the fundamental. And then you'd have the fourth harmonic, which would be equal to 7 times the fundamental. It all has to do with, again, the fact this has to be a node and this is an antinode. That's the only way you can get things fit in there. So those are the relationships between the dimensions of the tube and the frequency of the harmonics. Okay, so let's talk about the Doppler effect. And basically this is the effect on observed frequency because of the relative motion of the observer and the source. So let's give some variables here. V sub s, that's the velocity of the source. So that's where the sound is coming from. That's in meters per second. And then we have the velocity of the observer, V sub O. So that's the thing that's observing it, which is usually us or some person. Then you have the speed of sound, which we'll just call V. And you can find the speed of sound from the equation that we mentioned earlier. V is equal to 331 meters per second, square root of absolute temperature divided by 273 Kelvin. And then there is the frequency of the source. In hertz. And there's the frequency that the observer hears. In hertz. Okay, so that's it. Now, the equation is looking at the frequency that the observer hears, and it's a function, of course, what the frequency of the source is, and there's going to be the speed of sound in both the numerator and the denominator. Now, let's just think about, let's say the observer, here's the observer, and here's the source. If the source is moving towards the observer, so we'll say relative to the observer, if it's moving towards the source, then you're going to get the wavelengths are going to be compressed, which means lambda is going down. The wavelength's getting down because the waves are piling up on each other, and that means the frequency goes up. And if you think about something going by you, you hear doo 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 doo. So it's a higher frequency. So to get a higher, get a higher observed frequency than the source frequency, we're going to have to add the velocity of the observer to the speed of sound to make this fraction greater than 1. So V sub s is positive approaching observer. And obviously it's going to be as negative when it's what's the word? What's another word for approaching, going the other way? Not deapproaching, but going away from observer. So that would decrease the numerator, which would decrease the fraction. Now, in the denominator, you have the velocity of the observer, and what we're trying to do there is make the if we want the frequency to go up, then we want to subtract it from the denominator. So we're going to subtract, and that's when the V sub 0 is positive when observer is approaching source, and vice versa. Okay, so let's just think of a couple of scenarios. You know, the simplest case is the velocity of the observer equals 0. And in that case, the equation reduces down to the frequency of the observer. Here's the frequency of the source times the speed of sound plus the speed of the source divided by the speed of sound. So let's say the velocity of the source is 30 meters per second. Let's say the speed of sound, I'm just going to give it to you, 340 meters per second. And let's say the frequency of the source is 200 hertz. So the frequency that the observer hears is going to be 200 hertz. And this is so towards. So when the observer, the source is moving towards the observer, it's going to be 200 hertz times the speed of sound, which is 340 meters per second, plus 30 meters per second divided by 340 meters per second. And you can go ahead and calculate that. So you get 370 divided by 340 times 200. So that's the frequency that the observer hears is 218 hertz. And away you would get 200 hertz times 340 meters per second minus 30 meters per second divided by 340 meters per second. So that's 310 divided by 340 times 200, and you get 182. So that's kind of the simplest situation. I'm not going to do every particular scenario, but let's just do one where, let's see, the velocity of the, so this is the source. The velocity of the source is 20 meters per second this way, and the velocity of the observer is also this way. Let's say it's 10 meters per second. So in this case, the source is moving towards, but the observer is moving away. So what we're going to do is, because this one's moving trying to move towards the observer, even though it's going away, this V of the source is going to be positive. But in the second case here, V of the observer is negative because it's trying to move away. And you can kind of go back to if you held one stationary, what would happen? If the source is stationary and the observer is moving, if the observer is moving away, then the frequency is going to be lower because he's moving away, relatively speaking, away. So let's use this, well, we already have the numbers here. So the frequency the observer hears is going to be the frequency of the source times the velocity of speed of sound, which will keep it 340 meters per second, plus the velocity of the source divided by velocity speed of sound minus the velocity of the observer. So you get 200. We'll say that the frequency of the source is still 200 hertz. So you get 340 meters per second plus 20 meters per second. So it moving this way is wanting to increase the frequency, but the other one moving away is going to kind of compensate for that. So what you do is this one's going to be subtracting, if you go back to the original equation, but the number is negative, so it's negative 10 meters per second. So you get 200 times 340 plus 20 divided by 340 plus 10, and you get 206 hertz. So because the source is moving faster than the object, they are, relatively speaking, moving closer to each other, and hence the frequency should go up. And you can see if they had the same velocity, if they're both moving at 20 meters per second, there is no relative velocity between them, and therefore the observed frequency would be 200 hertz, the same. Now if you go the other direction, let's say they're both moving towards each other, relatively speaking. So if this were going this way instead, let's say the velocity of the observer is 20 meters per second. So in that case, the frequency that the observer hears, you get kind of a double dose. You get some increase because this one's moving towards this one, and this one's moving, and that one going the other way. So you'd have 200 hertz times 340 meters per second plus 20 meters per second. In this case, V of the observer is positive, so you'd have this is the velocity of the source. Now taking into account the velocity of the observer, so we're going to subtract because it's minus positive 20 meters per second. So you get 200 times 340 plus 20 divided by 340 minus 20, and you get 225 hertz. Now, let's say the velocity of the source equals 40 meters per second, and the velocity of the observer is 0 meters per second. So here, when you have 20 going one way and 20 going the other way, the relative velocity to each is plus 40. So let's see what happens in this case. So this is going to be positive. This is 0. So you get 200 hertz times 340 plus 40 divided by 340 plus 0. And you get 200 times 380 divided by 340. And you get 224 hertz. So it's not exactly the same, which is kind of interesting because you'd almost expect it to be that way. But it doesn't exactly equal that. But it's pretty darn close. Okay, so one of these variations, what you need to do is just make sure you think, all you have to remember here is that if things are moving towards each other, the frequency is going to be higher, and if they're moving away from each other, then they're going to be lower. And you can think about the case of the source moving towards the observer. They come to do, and the same thing would apply if the observer is moving towards the source. You'd hear the same thing. It'd be do. Okay, because initially they're moving towards each other, and then after they pass, they're moving away from each other. So I think that's it for sound. There's the beat frequency. We talked about that. But I guess I'm not going to put anything on the test about it. Okay. The next is reflection and refraction. So typically here we're dealing with flat surfaces in this chapter. So remember, the angles are defined relative to the normal. So we have a ray of light coming in and it bounces off, and this angle, theta sub I, which is the incidence angle, equals theta sub R. So that's the law of reflection, which we use in all our mirror calculations. And then you have the law of refraction, where you have a ray coming in from one material. A lot of times it's air, but it doesn't have to be. And the light is bent towards the normal associated with this surface. And if it's a flat surface, then it's pretty easy to find. So we call this the incident angle again. In this case, this is the refracted angle. And there's this relationship called Snell's law, which says n1 sine of theta 1 or equals n2 sine of theta 2. Now, in this situation, if we have the light coming in here, then theta 1 equals the incidence angle, and theta 2 equals the refracted angle. And this is assuming that you have, each one of these has an index of refraction. So if I assume that's 1 and this is higher, then it's going to bend towards the normal. Now you could have, you could go between two transparent medians where this is N1 is 1.2 and N2 is 1.5. In that case, well, let's see what happens. Let's say N0 here is 1. So if you came in here you would bend towards the normal, and then you would bend more towards normal as you go through each transition. So here's my normal. So you could use Snell's law across this boundary, and then you could use Snell's law across the second boundary. And the reason it's bending towards the normal, again, this is the incident angle for this boundary, and this is the refracted angle for this boundary. Then, if you think about these are straight surfaces, so this line normal is parallel to this normal, so the angle of refraction here ends up being the angle of incidence for the next one. But because we're going from from a lower to a higher value, it bends again. Now, if these were flipped around, then what would happen is that in the second case it would bend away from the normal. So it depends upon the relative values. So that might be an interesting problem. Do that where you have two interfaces, and I'm not sure which way I would do that. So just applying Snell's law, turns out, a lot of geometry involved, because you can create these right triangles. If I had these distant, the width of these pieces of glass, you would be able to tell how far the light ray, where the light ray would intersect the second surface if you wanted to do that. And one last thing. Well, before that though, when you have a situation like this, you can have part of the light is reflected and part of the light is refracted. So this would be theta sub reflect. I'd have to write out reflection because this is refraction. They both start with the letter R. So in this case, the angle of incidence equals the angle of reflection. But then the angle of refraction, you could use Snell's law to find that. And then if I asked you to find this angle, the angle between the reflected ray and the refracted ray, you could do that because you'd have a straight line here. This angle, that's the angle of incidence, it's the angle of reflection. And this angle would be the angle of refraction. And these two plus this have to add up to 180 degrees, so you could figure that out if you wanted to. So that might be an interesting problem as well. And the last thing out of this chapter is called total internal reflection. So remember what's happening here is you're going from some material of, let's say N1 is now 1.6 and N2 is 1. And if you take a light ray coming in to this surface, because I'm starting in the higher index of refraction material, instead of bending towards the normal, I'm going to bend, so that would be if they were the same index of refraction. If this N2 were higher than N1, it go this way, but if N2 is less than N1, it's going to bend like that. It's going to bend away from the normal. And you can use Snell's law to prove that. At some point, this angle, so let's move it over here. Let's call this the critical angle. Theta critical. We'll make it so the second angle goes like that. So remember, the scenario is that if you use Snell's law, N1 sine theta critical equals N2 sine of theta 2, but theta 2 is 90 degrees. So 90 degrees, and the sine of 90 degrees is 1. So you get N1 is the sine of this critical angle is equal to N2 times 1, which is N2. So the sine of theta critical is N2 over N1, or the critical angle for total internal reflection is the inverse sine of N2 over N1. Make sure your calculator is in degrees. So let's just look at an example here. Let's say N1 is 1.9 and N2 is 1. What is theta critical? Well, theta critical is the inverse sine of N2, which is 1, divided by N1, which is 1.9. And of course, it has to be that way because you can't have the inverse sine of a number unless it's between 0 and 1. So if you have those the wrong way around, you get an error. So it's pretty self-correcting as far as whether you use the right ratio. Okay, so you take the inverse sine of 1 divided by 1.9, and I get 31.7 degrees. So what that means is that if this angle here is greater than 31.8 degrees, then you're going to have internal reflection. So let's say this is 30, in this case for my example, 31.7 degrees. So what would happen if I then had an angle like that? So the lights, let's say this angle is 45 degrees. Well, what would happen is that this thing would bounce off such that the angle relative to the normal would be 45 degrees. So at 31.7, it goes up here, it goes parallel to the surface. Any angle greater than that, it's going to bounce back. Okay. Now, as far as lenses and mirrors are concerned, so I want you to be responsible for all of the scenarios for concave mirrors. So that means ray diagrams, how those work. We went through those in class. And also the equation, 1 over p plus 1 over q is equal to 1 over f. But for spherical mirrors, it's 2 over r. That's because the focal length is equal to the radius of the spherical mirror divided by 2. So, if we've done these mirror type problems, you got your focal point here and you've got your center. So this distance from there to there is r. So the focal length is half of that. And there are 3 scenarios, and I'm going to give you a ruler to work with, so I want you to draw a fairly accurate representation. So better than I'm doing here. So I'm just going to kind of do them quickly, but you might want to go back and look at what's going on here. So let's say this is the focal point, this is the center. The 3 scenarios are the location of the object relative to the center and the focal point. So a ray parallel to the axis of the mirror reflects through the focal point. One's going through the focal point, reflect parallel. That's the only 2 you need. And then that intersection point will give you the location. Also, the magnification, which is the ratio of the height of the image to the height of the object, is equal to negative q over p. So remember, this distance is p, this is q, this is f. These are all relative to the center of the mirror. So if this is negative, say p and q are positive, which is this scenario, then you get a ratio. And if p is further away than, in this scenario, p is bigger than q, then the image, this is the image, make sure you put an I for image, for object. So, the image is going to be smaller than the object because q is less than p. The negative means it's inverted. So what we'd say, in this case, real inverted smaller. So that's what the image is. It's real because it's on the same side as the object. It's inverted because it's upside down. Smaller because of the magnification. So that's the first scenario. The second scenario is where your object is located between the focal point. So this is the center, this focal point. So the rules still apply. So lines that are parallel to the axis of the mirror go through the focal point. Ones that go through the focal point go parallel to the mirror. I think I'm doing this quick, so it's you might want to do a better job of drawing all this stuff out, but the concept is correct. Okay, so this is the object. This is the image. You can see it's inverted. So it's real, inverted, enlarged. And that's because in this case P is, this is Q, this is P. So Q is greater than P, and hence the image is larger than the object. And the third scenario is like this, and I've drawn this out because the image is going to be behind. So here's a focal point, focal point, center. We're going to put the object right there. So if you go to the, there, it goes through the focal, bounce back through the focal point. Now through the focal point, it goes this way, and then it bounces off. The problem with that is that the two rays don't converge, so you can't have a image on the same side. So you reflect that back there, and you do that to there. So you extend these two lines that didn't converge to somewhere behind, and then you end up with the image back here. So this is Q, this is your image, this is your object, this is P, P, Q, and Q will be negative because it's behind the mirror. Therefore, the magnification is positive, negative Q over P, but Q is negative. So in this case, you get a virtual upright enlarged image. And remember, this is your eyeball, sticking your eyeball in there, and you're seeing this larger eyeball. It's also further away so that you can focus on that image. So those are the mirror situations. Then you've got your lens situations. So you've got this lens in the middle. And there's a focal point on either side So then, and then you have twice the focal length. So there's no equivalent to the center here. So this is 2f. This is f. This is f. This is 2f, and you've got 3 different scenarios. So let me just make 3 copies of this quickly, and I'll provide you with these drawings on the test, so you won't have to draw them. You just have to draw the images and objects and stuff like that. And actually, I think I'm going to draw where the image is. You just have to draw the lines. So here, instead of more than twice the radius, you put it past twice the focal length, or not twice the radius, still twice the focal length. For a mirror, it was the center as well, but okay, so you go parallel to the mirror till you get to the mirror, then you go through the focal point, or you go through the focal point to the mirror, and then parallel. And the resulting image is here. So object, image, this distance is P, this distance is Q, and this distance is F. And the same thing applies. 1 over P plus 1 over Q equals 1 over F. So that's the case where the object is more than twice the focal length. Then you've got the case where the object is between twice the focal length and the focal length, but the rules still apply. Parallel to the axis of the lens through the focal point, to the lens, parallel. So that intersection here of these points is where your image is. So you have the object, you have the image. This is P, this is Q. Also remember, magnification is the height of the image over the height of the object, which is negative P, Q over P again. So here you can see P is greater than Q. So in this case, we have a real inverted smaller image. In this case, we have a real inverted enlarged image. And the third scenario is where you're inside the focal length of the lens. So this is similar to the case with the mirror. You go to the mirror parallel to the axis through the focal point, and then if you go from the focal point through the end, you come up to here, and then you go parallel, and you can see that the two rays are diverging. So that means that you need to go the other direction. So this goes back that way, this goes like that, and the intersection of those two is where the image is. Okay, so this is the object, this is the image, and what we can say is it's virtual, because for a lens, if the object and the image are on the same side, the image is going to be virtual. It's virtual, it's upright, which means it's going to the same orientation, and it's enlarged. So this is, if you're on this side observing it, instead of seeing the object, you see the image, and it looks bigger to you. It also looks further away, so you can focus your eyes on it. Okay, so that is it for the final exam / test on the last bunch. So now I'm going to make the test up.